Okay. A vector space is a set of vectors and scalars with properties of closure, identity, and associativities, meaning that there's vectors form a closed set under vector addition. Identities, there's an identity for your vectors. There's a vector which, when added to any other vector, doesn't change that vector. Associativities, if you add if you have three vectors, it doesn't matter which two you add first. Okay, it doesn't matter if you add the first two first or the last two first. And the scalars also have these properties. And operations of scalars over vectors have similar properties. There's also distributivity of scalars over vector addition. And there we have a definition of a vector space. Okay, so you've seen these definitions, used them. We understand things like a set of vectors is a subspace, a subset of the vectors in the vector space is a subspace if it itself has all these properties, but really the necessary properties just closure. So we understand all that. Okay, now what we're doing is we're going to start with the biggest properties and work down to the smaller properties, kind of in the reverse order of the way the text and the course has developed. Okay, so we start with the idea of basis. If you have a vector space, it has a basis. The basis being a linearly independent spanning set. In general, it has many bases. Okay, in any basis, every vector has a unique representation. Now, I'm not writing out full statements here, but I'm trying to make full statements. So if you don't understand exactly what the statement was, it's a good time to stop the video and just make yourself into it. Every vector in the space has a unique representation. These are things we should understand, but they can still be a little bit fuzzy at this point. We're trying to pull it together from midterm exam. Okay, the dimension of a vector space is a number of vectors in a basis, and every basis has the same number of vectors. And now we want to talk about linear independence of a set. Linear independence of a set of vectors, and I didn't say a set of vectors because there's a lot that's implicit that I'm not going to write out here. But I'm saying it, so if you don't understand what I'm talking about, a set of vectors, again, you want to make yourself know that that's what I'm talking about. The only linear combination equal to the zero vector is trivial. What's that mean? The only way we can add up vectors in this, multiples of vectors in this set. Well, let's talk about linear combination just briefly. Again, implicitly, we know what that is, but a linear combination is a sum of multiples of the vectors in the set. Now, the typical representation C1v1 plus C2v2 and so forth equals your linear combination. Okay, the set is linearly independent. The only linear combination equal to zero is trivial, which means that you're just going to multiply every vector by zero and add up the results, which all have to be zero and will all add up to zero, to the zero vector. Okay. An equivalent condition is that none of these vectors is a linear combination of the others. Okay, so if the only linear combination equal to zero is trivial, then no vector can be a linear combination of the others, no vector in the set. And if no vector in the set can be a linear combination of the others, then the only linear combination that gives you zero is trivial. We should understand why. So think about why that's so if it's not obvious. It's one thing to know that it's true or to remember that it's true, another thing to understand why it's true. Then you really understand. Okay, now, if you have a linearly independent set, V1 through VR, let's say, then we can form the matrix where the V1s through the VRs are in the columns. Okay, so for example, if this is an n-dimensional space, and we have R vectors, then we have n numbers in each column here. So we have n rows of the matrix, and we have R columns. Each row is are numbers long. Okay. So again, the number of columns is the dimension of your space. Number of rows is a dimension of the space. And the number of columns is the number of vectors that you have in the space. Okay, well, if we were to reduce this, and if this is a linearly independent set, then you don't get a row of zeros. Okay, think about why that's so. And by reduced, implicitly, I mean Gauss-Jordan reduction. Okay. Now, if the dimension of the vector space is n, and if the set is linearly independent, that is, if B1 through Bn are linearly independent, then this reduces to the identity. Okay, because of course you're going to have n numbers in each column, meaning you have n rows, and you have n columns, meaning each row is n symbols long. And making this an n by n matrix, which can certainly reduce to I. It'll reduce to I if and only if this matrix reduces to the identity. So I can say if the dimension is n, then this. And vice versa. If this reduces to the identity, then these vectors actually have no. Vice versa doesn't really work. And there's some technicality. The idea is we're going to withdraw that comment. Okay. Okay. How do we represent a vector in terms of a set of linearly independent vectors in an n-dimension and linearly independent vectors in an n-dimensional space, meaning that these vectors form a basis. Okay. Well, representation of any old vector in the space in terms of a basis P is a set of vectors, C1, or a set of numbers, C1 through Cn, or the vector with components C1 through Cn. Such that the linear combination C1 V1 plus C2 V2 and all the way up to Cn Vn is equal to this. And that's the representation. And we represent that as Pxb equals the V vector. Okay. XB is the representation in terms of the matrix B, big B, capital B. Little b is just any vector in your space. Okay, so B has representation XB if XB equals P inverse times B, because PXB, that's this matrix product. Here's your P, here's your X, here's your B. If this set is linearly independent in the dimension the space is n, this reduces to I, meaning that these are linearly independent. And this reduces to I, these are linearly independent, so they form a basis. Because these are vectors in the basis. We put them, each vector forms a column, and you get an invertible matrix P, because of course, this matrix, here's your matrix P again, reduces to the identity. If this matrix reduces to the identity, then it's invertible. You get the inverse, multiply both sides by the inverse, and the representation XB is just going to be P inverse times your V vector. Now, it's important to remember from the very first chapter what happens with simultaneous equations. If you have more unknowns than you have equations, then you're going to end up with free variables. You're going to end up with an infinite number of solutions. If you have more equations than you have variables, then unless you have some sort of degeneracy where some equations end up being sums of multiples of others, then you can't expect a solution. If you have the same number of variables as equations, then if there's no degeneracy, you get a unique solution. And that all corresponds to things that we've already talked about with linearly independent sets and so forth. But let's flesh it out a little bit and let's move on into talking about rank and nullity a bit. Okay, so in an n-dimensional space, a linear combination of R vectors, V1 through VR, can be written C1, V1, and so forth up through CR, VR. Now, previously, I didn't write that out, but I implicitly assumed that you knew what that looked like, and I believe you do. Okay, but in case you didn't, there it is. That's what it looks like. It's a linear combination of your R vectors. Now, remember that V1 through VR have n components. Okay, so this would then be equivalent to n equations in R unknowns, where R might be more than n, might be less than n, might be equal to n, take in terms of what I just said about the systems of equations. So the equation C1, V1, and the later combination of your vectors V equal to some vector in your n-dimensional space, it's going to be expressed by this equation. Because, well, I'm assuming that we know why. Okay, because I've seen everybody write this out on more than one occasion correctly. So I think we understand why this is the case. So I don't need to go into a lot of detail. Okay, so again, here we have then, this is first of all an n by R matrix. N the dimension of your space, n rows, R symbols in each row. And again, represents n equations and R unknowns, just as we set up here. Okay, now, if R is less than n, what's that mean? It means you have more equations than you have unknowns. And that corresponds to fewer vectors here than there are in the basis. Well, it means that you don't have enough equations. I mean, yeah, you've got too many equations for your unknowns. So that means that maybe there are solutions for some vectors B, because certainly there are vectors that can be obtained as linear combinations V1 through VR, but you can't do it for all V, all vectors B in your n-dimensional space. So there exists some vectors B such that there's no solution. Another way of saying it is there exist vectors B which aren't in the span of V1 through VR. There aren't enough vectors in the span to span the n-dimensional space. Again, if R is less than n. Now, as we understand, the span of this set would be a subspace, and that's fairly easy to prove with closure. So we're talking about a subspace here in this case. It might not be an R-dimensional subspace because these vectors might not even be linearly independent. If they are linearly independent, then you have an R-dimensional subspace. If they aren't linearly independent, then it's a subspace of some dimension less than R. Okay, now if R is greater than n, I say, well, what does it mean for R to be greater than n? That means you have more unknowns because you have R unknowns. C1 through CR are unknown, means that this is bigger than this. This is longer than this. Means you have more unknowns than you have equations. When that happens, several things can be said. What I said before, if you have more unknowns than equations, then you end up, if you write out the system of variables, you end up with a lot of, if you write out the system of equations, you end up with a lot of, you end up with free variables. Okay, so you end up with an infinite number of solutions. That's inevitable if R is bigger than M. Another thing it means is, though, in terms of linear independence and so forth, is that there's some I less than or equal to R such that VI is a linear combination of the others. Meaning that this is a linearly independent set. Now, what do we mean by there exists an I less than or equal to R such that VI is a linear combination? Well, I is your subscript. I is less than or equal to R. Your subscripts run from 1 to R. That means there's some vector in here between V1 and VR that's a linear combination of all the others. So we want to understand that. And also, there exists non-trivial C1 through CR, such as V1 through VR, the matrix V1 through VR. Multiplied with that is 0. That is, this linear combination is 0, saying the same thing as this. This being a linear combination of these vectors. Okay. Well, I'm going to go on and talk about this. Let me pause for a second, see if I can clear my throat. Maybe my brain too. Okay, now, again, still talking about an n-dimensional space. Let's assume that R is bigger than M. Now, as we've seen, this means that this set of vectors, V1 through VR, is not linearly independent. There are too many vectors for the space. You have more vectors than you have dimension in the space, more vectors in this set than you have vectors in a basis. And all that goes together to show you and prove why at least one of these vectors is a linear combination of the others, or alternatively, that there exists a linear combination of these vectors. It's non-trivial, it's equal to 0. We want to talk about the rank of the matrix consisting of the vectors V1 through VR, and again, these vectors in the columns. Okay, so if it's an n-dimensional space, what you have is a matrix here with n rows and R columns, where R is bigger. So it's got more columns, it's wider than it is high. Meaning more variables than you've got equations. If you're setting up linear combinations. The rank of this matrix is the number of linearly independent rows. Okay, so if you row reduce this matrix, you've got more numbers in each row than you've got rows. So you kind of expect that if this thing is a random matrix, that it's not going to give you a row of zeros, but it might not be random. Okay. And if it's not random, it could well have rows of zeros, meaning that lots of these vectors might be linear combinations of others. Well, the rank is the number of linearly independent rows. If we reduce the matrix, we're just doing linear combinations of the row vectors. The row vectors, or the span of the row vectors, therefore doesn't change. So the rank for the matrix is the dimension of the space spanned by the row vectors. Now, that dimension can't be bigger than the dimension of the space that these vectors live in. No, it can't be bigger than m. Okay. If the rank is equal to m, then these vectors span V. They're not a basis because R is bigger than m. They have too many vectors to be a basis, but they do span V. In that case, the set of vectors V1 through VR can be reduced to a basis. That is, go ahead and find some vector in the space that's a linear combination of the others and just throw it out. And then look at what you got. Okay. If you still got more than n vectors, then you're going to be able to find another one. And you keep doing that. You keep throwing vectors out until you've got m vectors. And those m vectors will form a basis, assuming that the rank of this matrix is m. Remember also that the dimension of the column space is equal to the rank. Okay, so that you would then, if you reduce this matrix, you can tell which vectors you could select out of this set to form a basis. Okay, remember, well, yeah. Just make sure you understand that because we did that very recently. Okay. So that the whole idea of reducing a set of vectors to basis is an important idea and can always be done for a set of vectors whose number is greater than the dimension, but such that the rank of this matrix is n. If the rank is less than n, then the span of these vectors is a subset, a proper subset of V. That means it's a subspace, a proper subspace of V. Let's be sure we understand that what I'm intending this. Okay, yeah. If we let W stand for the span of this, then it's a subspace of V, it's a proper subspace. Okay, well, if the rank is less than n, even though R is greater than n, that just means that when we start throwing out vectors that are linear combinations of others within this set, we don't stop when we have n vectors. Because the rank of this matrix is less than n, that means that the vector, that the row space has dimension less than n, meaning that the column space has dimension less than n, meaning that the vectors in this column, that the vectors that form these columns span a space of dimension less than n. Okay, you can pick out some number fewer than n of these vectors, and they'll be linearly independent. Then the rest will be linearly dependent on that. Okay, well, if that's true, then just making another statement that this set can be reduced to a basis of W, which is what I just described. I think about that. Okay. Just throw these things out until you don't have any more linearly dependent vectors within the set. And that's going to be a basis of this subspace. In that case, the nullity of this matrix, which should have commas, okay, the nullity of this matrix equals the rank minus the dimension of W. Remember, the nullity I'm just looking for room to write the thing, of this matrix is the number of solutions of, I'm going to write it briefly. Number of solutions of AX equals 0, where X is this, A is this matrix. Okay, so the connection with rank and nullity. And if that isn't completely clear to you, you really want to review what the text and what your problem and so forth have shown you about rank and nullity, so that you're more comfortable with those ideas, because they're going to be very important for what we do in the second half of the course. Okay, well, there's more, but I'm going to have to stop here. And what I hope to be able to do, and we'll see if time permits, is to then look at the more basic connections, okay, the more fundamental connections in earlier chapters. But I hope you can see from what we've done here that everything goes back to systems and equations. And given that everybody did well in doing a representation of a given vector with respect to a given basis, I expect that that's the case. But within this context, I hope I'm going to be able to do a little bit more. I'm not going to, unfortunately, be able to do it today.